Good morning, developers. If you are looking for a description as to what Project Euler is, or you need one, want to know why I'm doing this, what the goals are, etc., please check out the first video in the playlist. I will link that in the description down below to that first video. That's where you would find this. Any journey through Project Euler, however far it goes, needs to start at the beginning, right? Problem one is the logical place to start. So if I click on archives, I won't show this again, but this is the list of all the problems. Number one, multiples of 3 and 5 is where we are beginning. And this is a very easy problem, okay? Do not worry, it will get very hard very fast. You will wish that we had some easier ones again very quickly. But I have copied this already and pasted it into a file called pe1.py for Project Euler 1, and I put it in a folder called Project Euler in the class repo. The reason I have done this is because for some reason they've done some funky CSS to get their numbers, and they're not copyable. I think it's because it's using a before content type deal. I don't know why they do that, but I will just read it to you over here. So the problem is this. If we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. So I've got a note here that a natural number is a non-negative integer. So it would be the numbers or the integers 1 through 9 in this case. Those are below 10. Sometimes a natural number includes 0. It's not relevant in our case because 0 is not going to be one of ours. Find the sum of all the multiples of 3 or 5 below 1,000. So let's look at this again. All the natural numbers below 10 are the numbers 1 through 9, or the integers 1 through 9. The ones that are multiples of 3 or 5, so if we take 3 into each of these numbers, which ones come out evenly? Those would be the integers, or those would be the multiples. 3 into 1, it does not go evenly, so it doesn't count. 2 doesn't go in evenly. 3 will go into 3 evenly one time, so that counts. We don't even need to check 5 because we only need one or the other. 3 will not go into 4 evenly. 5 will not go into 4 evenly, so we skip 4. 3 won't go into 5, but 5 will go into 5. 3 will go into 6 twice evenly, and so on. Okay, so that's how we get through this list. We sum these together, or we do 9 plus 6 plus 5 plus 3, and we get the number 23. So effectively what we've done is loop from 1 to 10, check to see, is this number divisible evenly by 3 or 5? If so, add the totals together, and we get the final number 23. Can we do that, or what is the sum if we went all the way up to 1,000? Okay, I told you it was easy. It's really pretty much just a glorified version of FizzBuzz, and it is a good place to start because, like I said, it helps us kind of think through how to look at these problems. They will get harder. We are going to start off with a variable called sum total, and I'm going to initialize that at 0. So we'll initialize we'll call it sum of our multiples if 3 or 5. So this is where we will keep that running total at. And as I already mentioned, we're going to need a for loop. The first one here is easy to do just in your head because it's only through 10. We're going to do for I in range. We'll start at 1 and we will go out to 1,000. Remember, in Python, the second number will not be included. So we will stop when we get to 1,000. We will not actually run that iteration. Just as a quick note, you could change this. You can add a stepper. That's a third argument you can pass range. Don't do this because we would start I off at 1 and then we would increment it by 2, which would jump us to 3, so on. We don't want to do that. You can put 1 in there, but it's already the default, so we don't need to do that. Come down to the next line here, and what we need to do is I divisible evenly, and I'll put that maybe in parentheses here, by 3 or 5. There is an operator that will handle this. You can pause me if you want to go look. I've got a video on it that explains a little bit more, but we are after the modulus operator. If I mod 3 is 0, or I mod 5 is 0, then it is a match. This is one of those multiples between 3 and 5. Let's hop over here quick and let's do a quick Python 3. I'll show you 3 mod 3 will return 0 because 3 divided by 3 is, the answer to that is 1. There's no numbers left over. If I do 4 mod 3, that means we are taking 3 into the number 4. Well, it'll go one time. So 4 minus 3, you still have 1 left over, so that's the number we get back. If we get back the number 0, that means it has gone in evenly, and that is the definition of a multiple. Okay, so this is our code. It is a match. We will run sum total plus equals I because this is a multiple added to our running total, and then at the very end here, we can print off sum underscore total like so. Let's go run our code. So it'll be Python against PE1. I am sorry, I've been on my PC a lot lately. It should be Python 3 for me. PE1, if you're on a PC, it's probably just Python. And this is the correct answer. It is 233,168. And if you want to see what they look like, we can print off the number I. Actually, let's do some F formatting here. So we'll do I is divisible by 3 or 5. You don't need to do this if you don't want to. It just will give us something to test against, I guess. Let's come over and give that a shot. Okay, there we go. So this is every single number. 999 would be divisible by 3. 996 is also divisible by 3. 995 is divisible by 5, and so on. If we add all of these numbers up, which is what's happening inside our loop, we get this this value down at the bottom. I'm going to comment out line 12 because that's going to get a little obnoxious. Since this problem is so easy, I will show you how to do it on one line. This is really common out there. If you go looking for Project Euler solutions, I'll put here ridiculous one-line answer. I would never do it this way really in almost any situation. I guess if we were in production and it had to be as absolutely tight as possible and I could prove that this was more efficient than what we wrote here, that is the only situation where I would do it. We can build a list. So you can do n for n in range 1, 1000. This right here will generate a list. So this is the loop. That part's exactly what we've got up above, except I'm using n here. We will call what we are on in the list n. Okay, so it's just simply going to put that digit into the list. So I'm going to do x equals, and let's print off x. So we are expecting this to be a list. Let's come back over, run our code, and you can see here it did just that. It printed off a list that it built with every single integer in there. Well, we can do one better, where should n be included or not? Well, we've got our loop here. We can drop in there an if statement and say if x mod 3 equals 0 or I mod 5 equals 0. This is the only condition under which this is going to actually get added, or I guess you should say n. So the for loop's going to happen every time. Each time through, before we put n in, it's going to run this statement. And if it evaluates to true, then n will get added to the list. So line 17 there, if we run our code again, I am sorry, I did x here, and this should be n. I apologize. I saw the x there, I guess, at the beginning. This should be if n equals, or n mod 3. Let's try that again. Okay, there we go. This time we get a list of every single number that is divisible by 3 or 5. So we've built a list. Okay, fairly straightforward. What do we do now? Well, we can set this equal to run the sum command. If you're not familiar with the sum command, it is a function that you handed an iterable, so a list, and it will try and add every single element together. It's a little bit like the sum command or function in Excel or Sheets or Numbers, whatever you might have used. You can sum a whole bunch of cells together. That's all that's going to happen here is we're going to run through, grab every element in this list, and if we punch it out, we get exactly the same answer. Okay, I would argue this is potentially not as efficient because we are building a list here and we don't need to build a list. Up above, the code is longer, but all we do is keep a running total as we look through. Down below, we do the same thing, but we also build a list which has to be stored in memory, and that would not be as efficient, but this certainly looks cooler than this answer here. Okay, great job. Project Euler number 1 complete.